Welcome to Data Science Without the Hype, a short presentation from Terminus Data Science LLC. I'm Derek Turk, consultant, president, and owner of Terminus Data Science. And today I want to share a short talk about what is data science without the hype, and what does it mean to those of us in the E&P industry. And in particular, for those of us launching data science teams, or other sorts of teams that engage with data science, what are some pitfalls and what are some opportunities in our industry? Data science is inescapable in the business and popular press. We see a lot of statistics and factoids and buzzwords. Here is one of my favorite, which is inescapable. I've seen this several times since I started in this field. 90% of all data was generated in the last 2 years, and I finally looked up a source on this. It's a research consortium, and this was from 2013. What could that sentence even possibly mean? It's so vague, right? What do we mean by data? And I suspect what was meant here is really digital data. But even then, how do you know? It's a factoid without context. And this is how data science or analytics is frequently presented in the press, without context, as sort of a set of whiz-bang facts and buzzword solutions, like maybe you've heard of Hadoop or MapReduce or NoSQL or deep learning. There's an endless array, and all of these have meaning and are useful tools for certain applications. But we kind of get this very vague, hype-driven picture, to the point that it can all really start to feel very meaningless. The press releases and the buzzwords and the new product launches and platform advertisements all begin to blend together. And while it can seem overwhelming, at the same time, a lot of it feels very fluffy and very marketing driven. There's kind of a famous quote in physics that it's not even wrong. We really can't even judge the veracity of some of the statements because they don't seem to refer to anything grounded in reality. And so it can seem very frustrating. That said, the fact that there's so much interest in data science and that there are so many new products and offerings being launched, while it can create a sort of frustrating blizzard of hype, it's really a good sign. It's a sign that there is some real value here. And if you scratch the surface and dig a little deeper, I do believe there is the potential for these techniques to fundamentally change the way we do things in the E&P industry. So here's what I do see. We do have a convergence of computing power, availability of digitized data, and algorithms that we can use to extract understanding from large volumes of data and recognize patterns and trends and relationships. And this lets us address problems with statistics and empiricism, which formerly we had to tackle from sort of first principles, or just not tackle at all. So things that were formerly seen as physics problems or economics problems, or for that matter, for those of you who watch some of the news in this field, Google has just released an AI that is beating world champion players at the game of Go, which has always been sort of a high watermark, kind of a game notorious for having a very large, complex space of possible moves. People spend their entire lives mastering this game, and it's seen as a very, very challenging and competitive game. Google has an AI that has trained sort of war game style on playing against human opponents and then sort of iteratively playing against itself. And this thing, it's called AlphaGo. It is beating grandmasters with strategies that they have literally never seen before. So it's pretty fascinating. We're doing some amazing things with these techniques. which is good for our industry, our E&P industry, because we have some challenging problems now, especially with unconventionals. We are seeing, more and more difficult physics, more and more difficult data acquisition. We're seeing a challenging price environment and a volatile price environment. And we are having to solve harder and harder problems with fewer resources, fewer human resources, fewer budget resources, fewer technical resources. So, what is data science really, and how can it help us? And for that matter, there's a lot of other words that go along with it. What is analytics? What is AI? What's machine learning? And how does it all relate to plain old statistics like a lot of us took in school? Well, I'm going to disappoint you a little bit because I don't have a great answer. I don't have a solid, concrete, gold-plated, write it down in the textbook answer. And frankly, I would argue no one does. I think these are all sort of loosely defined, overlapping disciplines with fuzzy boundaries. But I do think they have connotations. And so for those of us who have to sort of communicate what we do and sell the value we create, maybe there's some loose boundaries we can put on these. So kind of tongue in cheek, here are my connotations of each of these words. When I hear analytics, I think BI, I think dashboards, I think scatter plots in a web page, I think Excel, Spotfire, Tableau, these kind of tools. Not to knock them, but there's a ceiling. I don't see the word analytics affiliating to sort of the more deeply technical predictive modeling and machine learning approaches that we can now employ. Artificial intelligence, I think people just think of the Terminator when they hear AI, and so it's kind of got a sci-fi spook factor to it. The old joke about AI is that AI is a field that never shows any successes because as soon as it does achieve a success, that gets redefined out from under it. So AI is always what's 5 years out in the future. When we have self-driving cars, now they're AI. 5 years out, they'll be considered, oh, that's just, simple machine learning and neural networks or whatever. And we'll have redefined AI to mean, well, I want, Robbie the robot or whatever, or the Terminator maybe. Machine learning, I think it's a good phrase. I think people affiliate it with sort of an academic mathematical approach to applying statistics to form predictive models from data. And so I kind of see machine learning as a necessary subcomponent of what we do in this space. And statistics is really there at the foundation of it all. Statistics, people think of hypothesis tests and p-values, and that's part of it. But really, statistics is the mathematics of probability and sort of the mathematics of reasoning under uncertainty. So really, statistics is the language in which all of this is described at sort of the ground level. And so for my business, I choose to call what I do data science. It is a buzzword. It's not necessarily a priori the right answer, but to me it has the right connotation. And I view data science as kind of the conjunction of all these different maybe sub disciplines or fields. And so the definition I give my customers of what I do is sort of the use of empirical, data-driven techniques to understand patterns, model relationships, and fundamentally make better decisions. Really, as data scientists or people working in data science, our goal is not to model physics or to, build the lowest error regression model. It's really to get the maximum improvement in decision quality for our customers and sometimes our customers are ourselves. It's multidisciplinary. I think it includes elements of all those fields or maybe buzzwords that we talked about. And really critically, it is complementary to domain knowledge. And by domain knowledge for us, I mean the engineering, the geology, the finance, the actual disciplines that we are trying to augment with these data-driven techniques. And really it requires that context to be used responsibly and correctly and in a way that really creates value as opposed to confusion and chaos. It's also computational. And this is something I think that is a tension in the field because a lot of the products and platforms that are marketed at us sort of operate from an implicit premise of use this and you'll be abstracted away from the sort of underlying IT and software and computational substrate of data science. And I don't believe that's possible. I believe we can make it easier. But at the end of the day, we are applying techniques from computer science. We are organizing and manipulating data, and we've got to manage that in a way that runs inside the laws of our universe in a time frame that our clients can accept. And so fundamentally, that's a computer science problem, and there's no real escape, I think, for those of us in this field. So with that, I want to talk about kind of my clickbait headline is 3 tips for new EMP data science teams. And you'll see my asterisk. I have a couple more bonus tips in there. When I talk about EMP data science teams, I don't specifically mean your job title is data scientist or that your team is called a data science or analytics team. This can be we're a competitive intelligence group that's trying to use some of these techniques to do better analysis of our peers, to maybe drive business decisions, or maybe we're reservoir engineers and we're trying to apply some statistical techniques to forecasting. Really, any team that's touching on data-driven and statistical techniques, I think needs to keep these things in mind as they get started. And so they're all kind of framed in terms of goofy quotes, but I hope they convey some common pitfalls and caveats and things to strive for as EMP data scientists. So the first one I get a kick out of when Barack Obama took office as president. The news reported that he pulled his cabinet members, incoming cabinet aside, and he didn't say stuff, but effectively he told them, look, our policy is going to be first, don't do stupid stuff. And what I really mean by that is your reputation is staked on your EMP expertise. It is staked on your understanding of the domain of oil and gas production and operations. And so we cannot let ourselves operate in isolation from that context. It's the fastest way to lose the trust of our customers is to sort of miss the domain fundamentals. And I've got a story here, true story. A friend of mine who's a reservoir engineer at an EMP company was approached by that company's internal data science team, recently started data science team. And they wanted to forecast well production. They said, we've got an idea. We're going to try to forecast how a well will produce out in the future from its current production. We're going to use exponential smoothing, which is this statistical time series model that's pretty common in things like forecasting. Maybe if Walmart wants to forecast how many Furbies they're going to sell this Christmas, they punch in their Furby numbers from the last 5 years, and exponential smoothing lets them kind of build a weighted forecast out in the future, mostly driven by recent trends, but they can bring in sort of the past as well with a decaying weight and account for seasonal trends and so on. Well, here's a little demo I whipped up and sent my friend. I said, that probably isn't the greatest idea for forecasting well declines. And of course, we're kind of chuckling the whole time because as reservoir engineers, there's 80 years of prior art from an engineering standpoint, how do we forecast well production from data? I mean, this is, I think most of you listening will have heard of ARPS decline curves or exponential or hyperbolic declines. So this is ARP's paper from 1944, laying out the mathematics that we still use to do this in a way that's sort of maybe a little more anchored to engineering and has had 80 years of research and practical applications. So just that team, they thought they were doing a great thing, but they hadn't done even the most basic research into how do engineers already tackle this problem? What's actually the EMP domain knowledge that we need, not to stub our toe here, or not to reinvent the wheel. And so the moral of my story is do the research. When you build these teams, make sure there are people on the teams and involved in the teams and involved in the interface between these teams and their customers that understand they don't have to be deep, sort of best in the world experts, but they need to understand the domain they're working in. And it's really something to strive for. It's sort of how we get away from problems like correlation does not imply causation. For tip number 2, I stole the title of a book that was very popular a few years ago. The title was Program or Be Programmed. And I have a confession, I have not read the book. And from what little research I've done, it actually seems very sort of reactionary against the world of digital media that we live in today. So I don't have a comment on that, but I do like the title, Program or Be Programmed. And without being overly dramatic, the point I want to make here is that programming skill, understood broadly as software development and the ability to design software systems reliably, really is table stakes for the game of EMP data science. Because necessarily what we do involves processing data. We are required to collect data across multiple sources, transform it into different formats or interpretations or sort of computed variables, right? In building systems that can deal with errors and anomalies and unexpected conditions. And we have to be able to repeat procedures across big data sets and build our workflows in a way that they are reproducible, where we can come back in 6 months and update our analysis without having to sort of reinvent the world from scratch. And we have to be able to interface to other digital systems. We have to be able to visualize our data. We have to be able to access data that may be hosted on the web or stored in a database. And all of this means we don't have to be great programmers or programmers first and foremost, but our teams need to have some people who understand how to build software in at least a workmanlike and competent way. And there's really no escape. Despite all the visual and kind of drag and drop tools, some of these work really well for workflows that fit within sort of I guess the foresight of the tool designer, but they tend to fail in really opaque ways when we push those limits. Or at the very least, they tend to require falling back to a programming language or some scripting system to implement the more complex tasks. And so here's just a sampling of some of the common, maybe visual or high level or shrink wrap tools, and then the multiple scripting languages each one requires to go outside the box of what workflows are bundled up. And I don't really want to get into each tool or give recommendations, although I do have opinions on them. The point I really want to make is it's always required. You cannot escape from programming. And if you look at my list, you'll notice a theme here too. R, Python, SQL, JavaScript. These are really sort of open source or open standard, at least, languages that are used across the board. So my argument is if you are building a data science team, these skills are fundamental and they will serve you no matter what proprietary tool chain or vendor tool you end up perhaps picking up to speed up some of the work. So, you know, have that expertise on your team. Don't be afraid or don't feel like it's not your purview, that it's limited to IT or software developers, quote unquote. It's really fundamental to what we do. And finally, I want to encourage all of you to seek out quick, results and not sort of chase the hype cycle of some of these buzzwords. And kind of my dumb quote here is the Suave shampoo ad where they wash the lady's hair with the high dollar salon shampoo and then the $5 Walmart Suave shampoo, and she can't tell the difference, and if you can't tell, why should we? And what I mean here is that definitions matter less than results. We see a lot of talks and white papers, and they're great. I'm not knocking them on some of these very sexy topics, big data, deep learning. A buddy of mine was telling me he read an abstract about cognitive analytics. I don't know what that means. I don't know what that's intended to mean. To me, I think of, like my slide earlier, I just think of the Terminator. But it's really the little wins and the quick wins that can make your team heroes to your customers, especially when you're first starting out. A common question maybe that a data scientist might get in an oil and gas company. Does our competitor's completion strategy make a difference? Maybe they've hyped up, a different proppant selection or a different fluid loading or some change in their well completion strategy. Well, it doesn't take a lot of the sort of high dollar or high technical expertise techniques. Here's a simple strategy. Pull some recent production data, maybe from public sources. If you don't already have forecasts, maybe do some simple automated decline curve analysis. There are a lot of open source libraries out there or available tools that will do ARPS declines quickly on data. I know this because I've written one, actually written a couple. Um, Maybe pass that through a quick non-parametric hypothesis test, and maybe you find out, really there is no statistically significant difference in well performance. And so that probably took 2 or 3 hours to do, answered the question maybe from the board of directors, didn't apply any of the hot techniques, but your internal customer is thrilled because they got to answer this question. They got to say, no, what we're doing is just as good. We don't see any, what our peers are hyping up. Maybe there's no actual evidence that it makes a difference. Or maybe another one, how do geologic properties impact performance? So, and I kind of view this from this standpoint of a asset team engineer, completion or a reservoir engineer, because that's the world I spend a lot more of my time in. So from that standpoint, you reach out to the G&G team. They've got some mapped from core and from logs. They've probably mapped whatever petrophysical properties are available in the region, in the play. You kind of decide on some performance measures based on what data you have available. Maybe it's 6-month cumulative production. Maybe it's even if you're confident in your forecast, maybe it's even EUR based on your forecasted declines. Um, Build some simple predictive modeling technique on top of it. Maybe you can get away with a multivariate linear regression or even a k-nearest neighbor model or decision trees. Um, Visualize these response surfaces from your models with, maybe you've got some off-the-shelf tool. If you use Tableau, or if you've got you're familiar with some of the web frameworks for data visualization. And maybe it takes a week or two, and maybe you haven't done deep learning or cognitive analytics or whatever, but you've got some interactive tool that your completion engineers can use to optimize their designs, and that your geologists and reservoir engineers can use to kind of identify sweet spots. And in a week or two, you've delivered a lot of value, and hopefully the customer is enabled to do some things they could not previously do. So the moral is just really look for value over seeking out excuses to use the kind of newest hyped up tools and techniques. The tools and techniques will come, and yeah, when you have the problem where it makes sense, you'll know. But let the problem drive the solution, and not the other way around. I see I think one of the most common mistakes I see data science teams make is they sort of start out with a solution and then look for a problem and then get very frustrated when they can't communicate what they're doing to their customer because their customer fundamentally doesn't have a problem that maps onto the technique that's sort of, that they're trying to apply. So that's something I would encourage all of you to watch out for. All right, bonus tip number one, use free and open source tools. Frankly, they're better, they're cheaper, and they're everywhere anyway. Even the proprietary sort of vendor tools are starting to build more and more on open source underpinnings, right? Your SaaS project calls out to analysis scripts written in R, or your Spotfire project is scripted in Python. And so, learn the open source tools. Often you'll find they remove the need for the proprietary tool anyway. And here's kind of another case study, another true story, war story. They're also easier to debug. Nothing beats being able to look at the code or communicate with sort of a community of people that cares and has access to the code and has expertise. This was some work with a client of mine that uses a particular proprietary BI or visualization tool in-house. And so we had built a sort of Bayesian modeling technique and wanted to visualize the results in this BI tool. And our users were using some of the built-in functionality of the BI tool to filter their data before feeding it to our Bayesian model. And they were reporting that they were crashing when they started filtering data. And we kind of scratched our heads and said, man, this is built-in functionality in the BI tool. This it was before it even got to our code. So given that we were working with a closed source proprietary tool, we had to get a little creative in how we address the problem. And long story short, after a lot of head scratching and trial and error and sort of ad hoc debugging through the different scripting interfaces and API references and various things that came with this tool, we finally found the culprit. What the vendor had done is really gotten too clever for their own good. Part of their data model was the idea of a filter set, a set of rows that were removed from a data set. And they had actually built their own SQL parser as part of this BI tool. And internally, they were representing these filter sets as where clauses in SQL, and then running them through their own homebrew SQL parser to evaluate the filter. The problem is, number one, the expressions that the tool would generate if you came in and sequentially filtered out rows ended up being deeply, deeply nested. Each row you knocked out from the data added another level of nested parentheses. And of course, they had taken an off-the-shelf parser generator, Antler, and written what amounted to a recursive descent parser for SQL. And so without going into the sort of computer science or parser theory behind this, really what this means is that every nested expression in your SQL coming in corresponded to a nested recursive function call in the parser's execution. And so they knew that there was a potential of what we call overflowing the stack, and they didn't want that to happen. So they hard-coded a recursion limit of 800, which meant, of course, that our users blew up immediately as soon as they'd filtered 800 rows. So this is kind of insane, right? This tool was marketed as a way to do very simple ad hoc data filtering and analysis. And here we found out that baked into the tool is this limitation that if you filtered 800 records, you crashed. So we called up the vendor and sort of told them what we'd found. And of course, at first they didn't believe us, but eventually we were able to provide, enough reproducible crashes and enough information and logs that they believed us. And so a hot fix came out the next month, and we, very excitedly opened up the patch notes. And of course, they had just taken the hard-coded limit of 800 and increased it to int max, right? To 2 to the 31st minus 1. And so now what this really means is that the limit becomes a stack overflow, and we don't know at what point we'll hit a crash again. But at some unknown point, our users will just opaquely crash once again. So it really, not a great resolution. And this is frustrating because in an open source tool workflow, number one, we could have much more quickly found the problem, right? We would have had access to the source code, and we could immediately see, oh man, yeah, the way they're doing filtering does not make sense for our problem. We could have found it. We could contact, the maintainers, put in an issue maybe, or even just write our own patch and potentially submit it back to the project if we're feeling generous. And I know that seems far-fetched for day-to-day projects, but in my experience, it is surprising how frequently, whether you choose proprietary or open source tools, how frequently during ordinary data science projects you will actually hit these kind of odd limitations and unexpected limitations and flaws in the tooling. And so tool breakage is really not a question of if, but when. And so my advice is to choose wisely and choose tools where you can open them up and look under the hood if necessary. Bonus tip number two, one of my favorite talking points, and so, big data is a buzzword right now. And our industry does have some big data. But I like to tell people what we really have to solve is the problem of small, weird data. So, one of the common definitions for big data is this idea of the three V's, volume, velocity, and variety. Now, people keep adding V's. I sat in a talk a couple months ago where the guy was trying to push seven V's. No, I mean, no kidding. Seven V's of big data. But I don't know. I can't keep up with that. So we have some of this, real-time operational data, maybe LWD, MWD, seismic. The moral here is things that are high resolution in either time or space or both. And that gets into the big data world. A lot of what we do doesn't have volume or velocity, but it's got variety. It is like, I've got 12 frac stages worth of, well, kind of, I pulled some stuff from Frac Focus and it's kind of messy, mostly text. I've got monthly production data. I've got maybe, interpolated petrophysical properties. And so what we really get is different resolutions between our different disciplines of data, different formats, different structure. And so we've got to look for ways to get kind of some of our biggest wins from extracting meaningful features from this small weird data and then using statistical tools to integrate data across that resolution gap. And that's I'm going to leave it there for this talk, but this is one of my favorite topics. So, look for more on this in the future. Well, that's it. That's my tips. So, as I said previously, I do this for a living. I implement these techniques. I train, I coach. I'd love to work with you and your team. So look me up. We'd love to continue this discussion. Have a good day and thank you for listening.